implement those in the hack assembly language. So no high-level C-based languages provide two main ways of flow control. So we've got branching and loops. So branching, for example, an if-else type statement, is usually decision based, and the program can flow down different branches, typically depending on whether a relational operation is true. So if I is greater than 5, do this, else if I is greater than 10, do this, else, and so on. Then we've got loops. So a loops allow a portion of code to be repeated a specified number of times, and this typically depends on whether a relational operation is true. So while I is less than 10, you repeat something, or a for loop, for example, or even a do while loop. They're all the same idea, and they can all actually be implemented using a while loop. So there's these kind of two fundamental types. We've got the if-else type statement and then a while loop. So look how to implement an if statement in the hack assembly language. So in this very simple example, we can see if the contents of RAM 0 are greater than 100, we'll set the contents of RAM 1 to 5. So very, very simple. So you can see actually that's only kind of 2 or 3 lines of C. It actually ends up being kind of 12 lines of assembly. So you can see it's less efficient to write in assembly, and that's typically why we're writing high level languages. So the first couple of lines of the assembly, we just set the A register to be 0, and then so now A will contain the value 0 because that's the address of 0. So M will be pointing at 0. So we can just do D equals M and essentially copy the contents of RAM 0 into the D register. And then we want to load we need to load in this literal, and we know the only way to do that is through the A register. So we do at 100, that'll put the value 100 into the A register, and then by doing D equals D minus A, we'll end up subtracting we'll end up subtracting 100 from R0. So this is going to help us do this relational operation. So if we do R0 minus 100, we know that if R0 is greater than 100, the result of this subtraction will be greater than 0. So we're going to use one of the jump commands. So we're going to use jump if greater than. So we know if the contents of D is greater than 1, R0 must be 100, so that must be true. So by doing this command here, we're essentially saying if D is greater than 100, we want to if D is greater than 0, we want to jump, and that corresponds to when R0 is greater than 100. So we need to use these labels now. So in the preceding line, we've done at if true, so this is our own custom label. And this actually corresponds to the label down here. So we've got our label here, if true, and this bit of code here is essentially what goes on here. So this is the code that we want to execute if that is true. So that label, the labels don't get a line number or an instruction number. So the first instruction after that is instruction 8. So when this is assembled, this at if true is actually just equivalent to at 8. So that's essentially putting the instruction number 8 into the A register, and then if D is greater than 0, we'll jump to line 8. So if it's true, so this condition is true, we'll jump to here and we'll execute this code. So obviously that's false. So if it's true, we'll jump to here. And then if it's false, we'll just carry on. So if it is false, we obviously don't want to execute this code. So there's another label after this. I've called it cont for continue. So if it's false, we'll load that. So again, we've got instructions 0 to 11. So the next one will be 12. So the value when it's assembled that to become at 12. And then we're just doing unconditional jump. So 0 jump just means it doesn't matter, we just jump to whatever value is stored in the A register. So if it's false, we'll do this bit of code, then we'll jump past that code. So let's expand this, look at the if else logic. So now, it's the same, the first part's the same, but now we're just tagging on this else command at the end. So if that's false, we'll set the RAM1 value to 7, and you can see that's because of the colours here, so that corresponds to here. So it's the same in the previous example. So we've got this block of code here, which we want to do if it's true. So if that relationship's true, we'll execute this code, and then if it's false, so this part here is essentially the kind of false, what to do if this relationship is false. So we just put it here. So we check if it's true. If it is, we'll jump past and go to here and execute these lines. But if it's false, we'll execute these, which corresponds to RAM1 equals 7. And again, after that, we still need to put this another jump in, this unconditional jump, just to make sure after we've done the false, we don't want to execute the true code, so we need to jump past that and carry on. So in this case, the next instruction will be instruction 16. So at cont will be, when it's assembled, will become at 16, and then unconditional jump, 0 jump, will jump past the true statement. So while logic, so we're just going to do a simple example. We'll just add up 1 plus 2 plus 3 plus 4 plus 5, and we'll implement that using a loop. So this obviously is a very simple C code. So we've got a variable to store the kind of loop counter, a variable to store the sum, both initialized accordingly. And we've got our while loop, so we know while I is less than or equal to 5, we're just going to keep incrementing the sum by the value of I, increment I. So this will, grow in the loop 5 times, and as soon as it's false, it'll drop out of the loop and carry on executing. So now look at this code with these colours just to make it a bit easy to see. So the first line, int I equals 1. Here we just obviously created a variable, called it I, and assigned the value 1 to it. And this is done using these 2 lines in a hack assembler. So at I, m equals 1. So I is a user-defined symbol. So we know the starting address of user-defined symbols is 16. So when it's assembled at I, will actually become at 16. And then because 1 is an operation that the LU can do, we can just do m equals 1. So the LU will just output 1, and we'll store that in the RAM at the address pointed to by I. And we look at the next line, int sum equals 0, done in a very similar way. So we're going to do at sum, then m equals 0. So sum now is another user-defined symbol, but this is the second one. So I will end up being in 16, and sum will be in 17. And then because, again, 0 is an operation that the LU can do, we can just do m equals 0 directly. So look now how to implement that to a while loop. So I want to do while I is less than or equal to 5, I want to keep looping. So we need to first check the value of I. So we'll just put at I to get it into the A register, and essentially copy the current value of I into the D register. Again, load the literal value, so the maximum size of the loop here, 5. We'll create a literal for that value. D equals D minus A, similar to what we've done before. So we know we want to check it. So now once we've done this line of code, if that's greater than 0, we know that the kind of loop is finished. So if you do I minus 5 and you get a number greater than 0, this must be false, and so I want to jump out of this loop. So we've got this label down at the bottom, continue. So that continue kind of is referring to this part of the code here. So we'll just, if the value of d is greater than 0, we'll just jump out of this loop and we'll jump down to the bottom. So we'll just skip out of here. But inside of the loop, we need to implement sum plus equals I. So again, we'll get the current value of I, store that in D, and get the current value of sum, and just add on. So we can do m equals d plus m, and I'll just add on I, so we can do that easily enough. Then I plus plus, yeah, we're just loading I, then we can use the operation m equals m plus 1, so that will just increment I by 1. So you've got to be careful, because there's actually some conflicting use of the A register, so if you're not careful it's very easy to put bugs into your code. So we can see that the A register, we use it when we want to select a RAM location for a subsequent C instruction involving M. We need to put this, we need to load the A register with a value, and then if we do M equals D, for example, that will store RAM 15, whatever value is in D. So that's how we use it to address RAM. And then we also use it for selecting an instruction memory location, so ROM. When we're going to do a jump. So for this kind of code here, we're going to put a value in the A register, and then supposing this jump is true, we'll jump to whatever value is stored in the A register. So we can use the A register for addressing RAM and ROM. So to avoid this conflicting use, you need to make sure that you don't use C instructions with a jump that also contain a reference to M. So in this example, so this is an example, you don't want to do something like this. You never want to have a situation if you've got M and a jump. Just don't do that, because if you look at this instruction, we'll put at 67 is going to put the value 67 into the A register, and then we'll end up with D being equal to the whatever is stored in RAM 67, and then if that ends up being greater than 0, we're going to jump, we'll jump to ROM. So the next instruction, what will get executed, will be ROM 67. And you can see there's no kind of relationship between RAM and ROM. The data's not aligned, if you will. The instructions, nothing to do with the actual value, the memory location in RAM. So that'll essentially copy RAM 67 to the D register and then jump to instruction 67. So it doesn't make any sense. You want to avoid any situation where you've got a reference to M and also a jump condition.